So in this lecture we go from a finite subgroup of elliptic curve to isogeny. So say we are given theta as a subgroup of elliptic curve, and this theta is a finite subgroup. So from this theta we can now construct a separable isogeny. So then there is a unique elliptic curve E prime, and there is a separable isogeny phi from E to E prime such that kernel of phi is precisely this finite subgroup. So to prove this theorem we need a fact. So you know that corresponding to every algebraic variety there is a function field. So we can talk about transcendence degree of this function field. So transcendence degree of a function field L of an n-dimensional algebraic variety over some ground field K is n. So n-dimensional algebraic variety has transcendence degree n. So this translates for the case of elliptic curves or just curves, this transcendence degree is 1 because they're just curves, they have dimension 1. So the transcendence degree is 1 for curves over K. So this we will need shortly. So this theta, which is a finite subgroup, so this is a subgroup of elliptic curve E, so it consists of a bunch of points. So it acts on the function field of KE via the translation map for every point. So this is just this map tau of P which just discussed in the previous lecture. So translation map for every point in theta. So each point will give rise to an automorphism of K of E. Just like in the previous lecture we showed that this translation map gives rise to an automorphism of K of E. So from here we can find this K bar of E in the closure of theta. This be the fixed field. So this is the fixed field of K bar of E. So all these points they fix something. So we have a fixed field. So from Galois theory we have this degree of extension is Galois because this theta is a fixed field. We are just finding the fixed field, and this is precisely degree as theta because we are just taking all the points which are fixing. So every point fixes it. So this degree of extension is just theta from Galois theory. But using this fact we know this transcendence degree is 1. So transcendence degree is 1. So therefore since this transcendence degree is 1, therefore there is some unique smooth curve C over K bar, and there is a finite morphism phi from E to C. So this transcendence degree is 1. So C over this fixed field is 1. And now you can say phi star of K bar of E is this. So you have the curve. So this transcendence degree has given us a curve C. So we are good. And also this degree of phi is this degree of extension which is precisely theta as we have seen here. So this is precisely theta. So this is just theta. So you can see the degree of phi is equal to kernel. So this degree of phi we have proved before is equal to the size of our kernel, and this is equal to our size of theta. So there's nothing much to be done. We just followed the translation map and we followed this fact. So translation map gave us this Galois extension with degree theta, and then we knew that the transcendence degree was 1 of this over any ground field K bar because transcendence degree is 1 for a curve. We could find a map like this so that this phi star of K bar over C is just this fixed field, and then we know that this degree of phi will be like this. So yeah, so nothing much, just copying the definition. The only problem is we have to show that this curve does have genus 1. So for that we will have to use this Riemann-Hurewicz formula for unramified morphism. So again, because we have a separable isogeny, we can talk about unramified morphisms. So that is twice genus of E minus 2 is degree of phi times twice genus of C minus 2. So genus of elliptic curve is 1. So 2 times 1 minus 2. So this side becomes 0. So degree of phi is non-zero because it is precisely equal to the number of elements in a finite subgroup, which is non-trivial. So this is a non-trivial subgroup. So this is non-zero. So you have to say twice genus of C minus 2 is 0. So genus of C is 1. So again, this you can find on page 75 of Silverman. there is a small typo in the book regarding this, so this is the correct formula, and you can put a 2 in front of the formula in the book. So this is page 75 of Silverman's book, Arithmetic of Elliptic Curves.